بعدي أمونة متخربش عندك مالها شو عندك روحي أمونة روحي أنا نخدم بنتي روحي ولد من بعد ديري كي تشوفيني روحي هادي حبس كونيكسيو 40 دقيقة ما نعرف ليه يسمعوا كي نزيد البارتي الآخر والله لا فيه يدي لسوي والله لا يطلع سوايع أصير 40 دقيقة ذيك فرشتوها معايا قاع صي قاع دوك تصير أمين يا ريح يا بنتي كيف ما خرجت عاودي الدخلي عاودي ها فوتي بالليلية الباب هنا أمونة روحي بنتي روحي ها عندك صحة بالليل صح روحي بالليل يا بركان صح سمعت روحي بنتي لا ما تخربينيش روحي بنتي روحي الناس يجون روحي بنتي خليني نخدم Okay, hello guys. Let's continue. Point level, switches and safeties. Flow, capacitive, vibrating fork, and microwave switches provide discrete level states. They are used point level switches, float capacity, vibrating fork, microwave, provide reliable discrete signals for low-high alarms and safety interlocks. Select based on media, coatings buildup, temperature, and record fail state. Failsafe open or closed. For safety critical overfill or low-level trips, test proof functions regularly to maintain seal claims. Consider mechanical robustness and mounting orientation relative to flow turbulence. Example: use dual vibrating fork high-level switches on transfer tank to provide redundant overfill protection with voting logic. 12. pH and ORP measurements. Glass electrodes measure potential related to hydrogen ion activity. Temperature compensation is essential. Reference junctions clog in dirty processes. Use flowing or double junction designs. ORP then detects oxidizing, reducing tendency, and is process specific. Maintain with regular cleaning, buffer checks, and storage solutions. Keep cable length short and well shielded to avoid noise. Glass pH electrodes measure H plus activity and record temperature compensation and correct storage. pH 4 or KCl solution. To avoid drift, dirty or process heavy steams, full reference junctions. Use double junctions or flowing reference electrodes where contamination is expected. ORP gives oxidation reduction trend, not a universal contaminant number. Interpret in process context. Regular cleaning, buffer checks, and electrode replacement skills are essential for validity. Example: in produced water treatment skid, install a flow through pH sensor with automatic cleaning and run daily buffer checks to ensure chemical dosing accuracy. Conductivity and resistivity. Conductivity sensors use contact cells or inductive coils to measure ionic strength. Temperature strongly affects readings. Apply compensation with the correct coefficient. High purity water uses resistivity units, mega ohm in centimeters. And special sensors, cell constant must watch the application. Fooling changes it over time. Calibrate with certified standards and document calibration factors. Conductivity sensors, conducting or inductive, measure ionic strength, temperature compensation in mandatory alpha coefficient. For ultra pure water, use resistivity measurements in mega ohm centimeter and special cells to avoid contamination. Fooling alters the effective cell constant, scheduled cleaning, and recalibration. Always calibrate with certified conductivity standards and track cell constants. Example: in boiler feed water control, use temperature compensated conductivity transmitter with routine calibration to avoid carryover and scaling. Paramagnetic O2 analyzer are fast and accurate for combustion control. NDIR handles CO2/CO by measuring infrared absorption band. Electromechanical cells measure toxic gases like H2S. They have limited life and require BAM tests. TDL analyzers provide in-situ measurements with minimal maintenance. Sampling, filtration, and conditioning are as important as the sensor itself. So
So
the paramagnetic oxygen analyzers are good for combustion control with fast response, and the air is the standard for CO2, CO due to selective air absorption. Electrochemical cells are compact for toxic gases, H2S, but have finite lifetime and require BAMS test. Tunable diode laser TDL analyzers. So TDL analyzers provide highly selective in situ measurements for difficult species. Sampling systems, filters, heated lines, calibration gas manifolds are as critical as the sensor for reliable readings. Example, for flare gas monitoring, install an NDIR for CO2, CO, and a separate IS protected electrochemical H2S cell with periodic bond test. Process gas chromatographs, GC. GC separate components by retention time and quantify via detector response. They need stable carrier gas, precise temperature control, and clean sampling use stream. Use stream switching manifolds and automatic calibration with standards. Cyclic times range from seconds to minutes, align with control needs. Custody transfer applications require strict validation and audits. Gas chromatograph separates gas mixture and quantify components by retention time and detector response. They are indispensable for composition and UV LHB calculations. GCs require clean sample systems, stable carrier gas, and controlled oven temperatures. Install steam switching and auto calibration with certified gas standards for reliability and minimize drift. Cycle times vary. Ensure the GC's analysis time matches control and allocation requirements. Example, in an upstream gas plant, a GC with a proven sample conditioning and a fast cycle is used to calculate NGL split and custody transfer allocation. Sampling systems. Poor sampling brands good analyzers designed for representativeness and safety. Use heated lines for condensables and maintain isokinetic conditions if needed. Avoid dead legs, absorbent materials, and log residence times. Add filters, coalescers, knockout pots, and bypasses for maintainability. Document PNIDs and sampling points with traceable valves and tags. A representative sample is the foundation of any analysis. Poor sampling bias all downstream data. Designed to avoid dead legs, long residence times, or condensation, heat and isolate lines for condensable steams and maintain isokinetic conditions when sampling flowing gas liquid. Include knockout pots, filters, and bypasses so analyzer can be serviced without losing samples. Tag and trace sample lines on PNIDs and ensure safe pairs venting arrangements. Example, for wet gas samples to GC, use heated sample probe, heated transfer lines, and coalescers to remove liquids before the GC. Control valves, trim and characteristics. Valve trim, plug, seat, cage. Defines capacity, noise, and cavitation behavior. Linear equal percentage, and quick opening characteristics fit different loops. Rangeability indicates usable control span. High rangeability helps in varying loads. Positioners improve accuracy and overcome friction and dead bend. Choose body trim materials for corrosion, erosion, and temperature. Valve trim choice determines capacity, cavitation resistance, noise and controllability, match valve characteristics to process gain. Equal percent is common for pressure or flow loops with large changes. Rangeability and inherent flow characteristics affect how the valve behaves at low flows. Choose trims and positioners to meet turn down. Select materials to withstand erosion or corrosion and consider anti-cavitation stages where large DP exists. Example: in a high-pressure drop choke feeding separator, use multi-stage anti-cavitation trim to prevent seed damage. Actuators and positioners. Pneumatic actuators are common, fast, and fail-safe with springs. Electric actuators sit slow movements and high thrust but need protection. Smart positioners are diagnostics, hysteresis, stiction, travel limits, air quality, dry and clean, and supply pressure stability are critical. Always define fail action, fail close, fail open, or fail in place. Pneumatic actuators are preferred for speed and fail-safe spring action. Electric actuators give precise control and high thrust but require electrical protection and sometimes gearbox maintenance. Smart electropneumatic positioners are diagnostics like travel time, hysteristics, and valve signature. Integrate these to CMMS for condition-based maintenance. Ensure instrument air quality, dry oil free, and stable supply pressure for repeatable performance. Define and test fail action, fail open, close, in place, and ensure the logic enforces it under lows of power scenarios. Example: feed a smart positioner to globe valve on a feed controller to track friction and trigger maintenance when travel time degrades. Cavitation, flushing, and noise. High pressure drop across valves can cause cavitation and flushing. Cavitation damages stream via pitching and noise. Flushing erodes downstream. Use multi-stage streams, anti-cavitation cages, or split range control to reduce delta P. Slide valves to operate near 60 to 80% open at normal load. Verify sound power predictions, PS, site limits, and add silencers if needed. Cavitations occurs when local pressure drops below vapor pressure and bubbles collapse violently, causing pitting and nose. Flushing, it is permanent vapor formation downstream. So the flushing erodes stream and downstream piping. Mitigate via staged pressure reduction, multi-stage streams. Pressure recovery regions or limit operating delta V via split range control. Valve sizing to operate near mid-stroke, reduce stream wear and improves controllability. Acoustic silencer limit noise emissions. Example: on a high delta P boil off control, replace a single stage globe trim with a 3-stage cage trim and reevaluate sound levels. Loop fundamentals. Proportional PID. Proportional control corrects proportional to error but leaves offset. Integral removes offset but accumulating errors. Too much causes oscillation. Derivative anticipates change but amplifies noise. Filter it. Start with conservative gains, then refine by trial or a method like lambda. Always include output limits, anti-wind up, and bumpless transfer. Proportional corrects proportionally to error but leaves steady state offset, as we said. Integral removes offset by accumulating errors but risks wind up and oscillation if aggressive. Derivative anticipates change but amplifies noise and must be filtered. Practical tuning stars conservatively. Use relay, Ziegler, Nichols, or model-based methods lambda, and then refine with process knowledge. Always set out limits, anti-wind up, rate limits, and bumpless transfer for manual auto transition. Example: for level control and on surge tank with the slow dynamics, prioritize P and I. Keep derivative low or disable and include bumpless transfer for operator intervention. Okay guys, we will continue in 15 minutes. Stay tuned, drink coffee and get some rest, and we will continue later. Thank you for watching. Hello? 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 Test, hello? Test, 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 test. Okay, guys, let's continue for 21st topic. Advanced control, cascade, feedforward, split range. Cascade causes a fast inner loop to protect slower primary variables. Feedforward measures disturbance and corrects preemptively. It still needs feedback. Split range maps one controller output to two final elements for wide rangeability. Ratio control maintains constant proportion between flows, document strategy, limits, and interlocks on the PID and logic sheets. Cascade control nests a fast inner loop. Example, valve position or flow. Under slower outer loop to speed disturbances rejection. Feedforward uses a measured disturbance like inlet flow to pre-correct the controllers, reducing dependence on feedback, but it still needs feedback for offset. Split range lets one controller drive two final elements. Example, two valves across different ranges for wide capacity. Ratio control locks two flows together. Fuel to air chemical dosing. Example, implement cascade level control where the slave loop controls the inlet flow valve and the master loop adjusts set points based on downstream demand. Signal conditioning and filtering. Use damping to smooth noisy signals but avoid excessive lag. Low-pass filters are common. Define cutoff by process dynamics. Square root extractions is required for DP flow. Linearize only once. Apply calibration trims only after verifying hardware issues. Record all adjustments and keep as found as left data. Dampen smooth noisy signals but introduce lag. Choose filter time constant to preserve control performance. Low pass filters are common. For DP flows, use square root extraction to linearize before control mode. Hardware conditioning, amplifiers, surge protection, common mode rejection is preferred to software only fixes. Always verify the effect of filtering on loop stability during tuning. Example, when DP flow has pipe vibration, noise, add low-pass filter at transmitter and reevaluate controller tuning to avoid sluggish behavior. Scaling, ranging, LRV, URV. Define LRV 4 mA and URV 20 mA with engineering units and time. Ensure the DCS PLC scaling matches transmitter scaling. Consider normal operating range, alarms and trips when choosing span. Leave headroom to avoid saturation at upsets. Test with simulated signals and field verification. Correct scaling maps sensor electrical range to engineering units in PLC, DCS, and HMI. Mismatches cause wrong displays and potential trips. Define LRV and URV 4 to 20 on-field devices and in the controller. Record units and tolerances. Select spans so normal operation uses central portion of range for resolution and headroom for excursions. Simulate and test with handheld calibrator to confirm end-to-end scaling. Example, a pressure transmitter is ranked 0 to 100 bar, but controller was set 0 to 10 bar. Fix scaling to avoid false high alarms and trips. Marshalling, I/O and wiring. Use marshalling cabinets to decouple field terminations from I/O cards. Keep clear labeling, fields, and wire color codes per standard. Separate analog, digital, and high voltage routes. Maintain band radius and shielding. Document loop drawings with terminal numbers end to end. Include surge protection and spare capacity for expansion. Marshalling cabinets decouple feed termination from control room I/O modules, simplifying replacements and labeling. Use clear field IDs. Maintain wiring diagrams that map field tags to marshalling to terminal to marshalling terminal to I/O card. Separate analog, digital, and power wiring physically to avoid crosstalk. Follow band radius and grant practices. Include spare channels and surge protection in marshalling for future expansion. Example: during site acceptance test, trace each loop from field junction box to marshalling and confirm terminal numbers match loop drawings. Grounding, shielding, and noise. Implement signal point signals grounding to prevent loops. Connect cable shields at one end only unless using intrinsically safe system that requires specific bonding. Keep power and signal cables physically separated. Use twisted pairs and avoid VFD noise by physical routing and ferrits. Verify earth resistance and bonding continuity during commissioning. Single point signal grounding avoid ground loops in analog systems. In large plants, use equipotential bonding and structured grounding plans. Connect cable shield at one end unless intrinsically safe or specific cable standards require different bonding. Physically separate power and signal cables. Use twisted pair and shielded cables and ferrits near VFDs to reduce noise. Verify earth resistance and bonding continuity in commissioning. Example: persistent noise on thermocouple near VFD was resolved by routing the TC cable away from VFD power lines and adding ferrite cores. Power supplies and redundancy. Industrial instruments often use 24 VDC with battery backed USB, UPS, backed UPS. Redundant supplies and O-ring diodes increase availability. Monitor supply health and load margin. Derate with temperature. Use separate feeds for critical SIS, VS, BPCS. Label and test DC distribution breakers and fuses. 24 VDC is the standard for field instruments bucket with UPS and redundant supplies for critical loops. SIS emergency valves. Use O-ring diodes or load sharing modules to provide hot redundancy and avoid single point failures. Monitor supply voltage current and leave headroom to avoid brownouts when loads change. Segregate critical SIS supplies from BPCS to meet safety, separation, and availability targets. Example: instrument air and 24 VDC for emergency shutdown valves are on separate redundant supplies with automatic switchover and alarmed low voltage trips. Hazardous areas and protection concepts. Class division or zone systems define gas that explosion risks. Intrinsically safety limits energy. Explosion proof contains ignition. Increased safety avoids arcs. Barrier isolators must match entity parameters and cable lengths. Marking AXEIA, 2C, T4, etc. Encode gas group and temperature class. Keep inspection schedules and maintain certifications and doses. Class division or zone systems classify hazardous areas. Select equipment with appropriate AX marking, intrinsically safety limits, energy in circuit. Explosion proof contains an ignition in enclosures. Increased safety means improved design to avoid arcs. Match barriers, isolators to device, entity parameters, and cable length to maintain IS approval. Maintain dossiers and inspection certificates and schedule recertifications. Example: Where sensor in zone 0 is required, use an AXEA rate transmitter and IS barriers in the marshalling cabinet. SIS, seal, and functional safety. Safety instrumented systems reduce process risk with independent layers. Seal targets are set by risk analysis and verified by PFT average calculations. Proof testing restores reliability, intervals balance risk and downtime. Separation from BPCS prevents common cause failures. Document SRS, cause and effect, and test records rigorously. Safety instrumented systems are independent layers to reduce risk. SIL levels 1 to 4 correspond to record reliability targets determined by risk analysis. Define SRS, cause and effect metrics, and proof test intervals that balance risk reduction and maintenance downtime. Proof testing and spares planning are part of maintaining the achieved seal. Ensure physical separation from BPCS to avoid common cause failures and document all testing. Example, an emergency shutdown. An emergency shutdown valve with seal2 requires redundant solenoids and periodic proof tests recorded in the safety management system. PNIDs, loop diagrams, and tagging. PNIDs show instruments, lines, and control logic at a functional level. Loop diagrams provide wiring and terminations from field to I/O. Tagging allows ISA, IEC conventions, stay consistent across document, keep a master index with service, range, and calibration data, read line changes during commissioning, and close out with as-built. PRIDs provide functional views of piping, instruments, and control logic. Loop diagrams show wiring details from field to I/Os. Use consistent stack conventions, ASI, IEC, so every instrument is uniquely identifiable across documents. Maintain a master index that links stacks to datasheets, ranges, and calibration history. Read line changes during commissioning and reconcile to as-built drawings promptly. Example, during commissioning, an updated impulse line routine is redlined on PNIDs and later incorporated into the CAD master with revised tag notes. Calibration and metrology. Calibration compares an instrument to a traceable standard and adjusts if needed. Always record as found and as left environmental conditions and uncertainties. Use 5-point up-down checks across span to detect hysteresis. Field calibration needs stable temperature and power. Bench calibration offers better control. Maintain certificates and recall cycles in CMMS. Calibration compares instruments with traceable standards to quantify and adjust errors. Record as found as left values, uncertainties, and environmental conditions. Use multi-point checks to detect hysteresis and non-linearity. Bench calibration is best for accuracy. Field calibration is practical but requires stable references. Track certificates and recall intervals in CMMS and include calibration acceptance criteria. Example: calibrate flow transmitter using calibrated flow prover and log as found as left values into the CMMS. We will continue in a few minutes. Stay tuned. Thank you for watching. Test, 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 test. Test. Hello. So let's continue the rest of topics. Commissioning, FIT, SIT, loop checks. FAT verifies functionality on test bench. SIT confirms in the field. Loop checks prove signal integrity from sensor to graphics and interlocks. Simulate trips and alarms, documenting responses and times. Use bench leads and track NCRs to closure. Protect devices after testing to avoid damage before startup. FIT factory acceptance test verifies equipment function before shipment. SIT site acceptance test confirms correct operation in situ. Loop checks validate signal integrity and response from sensors to control room graphics and to interlocks. Simulate trips and document response times and operators' actions. Use bench lists and NCR tracking until closure. Protect devices after testing to avoid damage or tampering before startup. Example, a pressure loop is simulated with a calibrator during SIT to exercise alarms, shutdowns, and confirm trip timing with ESD system. Troubleshooting playbook. Start with basics, power, polarity, fuses, and wiring continuity. Compare transmitter, local display vs DCS to isolate I/O issues. Use handheld communicators or software for diagnostics. Look for process side problems, plugging, leaks, or damaged impulse lines. Change only one variable at a time and long finding. Start with electrical basics, power, fuses, polarity, wiring continuity, and terminal markings. Compare local transmitter display vs DCS value to isolate fields vs I/O failures. Use handheld communicators, HART, oscilloscopes, or software diagnostics to find noise, intermittent faults, or ground loops. Examine process side problems, blocked impulse lines, gas pockets, plugged sample filters before changing control logic. Change one variable at a time. Log steps and revert if no improvement. Example, when DP filter reading jumps, isolate and blow down impulse lines to remove trapped air pockets before changing transmitter setting. Material compatibility and weighted parts. Select weighted materials for corrosion, surface, and erosion. 316 is common but not universal. Consider duplex, hasteroid, or mono elastomers, FKM, APDM, MBA, matter for seals and temperature limits. Diaphragm seal fill fluids must match process temperature and vacuum. Consult corrosion curves and process data sheet. Select weighted materials for corrosion resistance, service, and erosion. 316L is common but not always suitable. Elastomers have different chemical and temperature limits. Match them to process fluids and ambient conditions. Diaphragm seal fill fluids must set operating temperature and any vacuum conditions to avoid vaporization. Consult chemical compatibility charts and datasheets for long-term reliability. Example, for chlorinated Process steam, select the Hastelloy diaphragm and PTFE phased elastomer seals. Environmental ratings and closures. IP NEMA ratings define protection against dust and water, consider UV, salt fog, and temperature extremes for outdoor installs. Use sunshades, heaters, or purged enclosures where needed. Cable lengths must match area classification and sealing requirements. Keep desiccants fresh and breathers clear. Choose enclosures with appropriate IP ratings for dust and water ingress. Include UV and salt fog considerations for coastal sites. Use sunshades, heaters, or pairs enclosures for extremely high low temperatures and for condensation control. Cable lengths must be compatible with area classification and ensure proper sealing. Keep desiccants fresh and check breathers during maintenance. Example: outdoor analyzer cabinets often requires IP66 NEMA 4 times with purge and heater for desert summers and winter nights. Wireless instrumentation. Wireless HART ISA 100. Wireless networks reduce wiring costs and enable hard-to-reach measurements. Mesh topology improves reliability via redundant paths. Battery life depends on update rates, network quality, and temperature. Use gateways with the proper antenna placement and site surveys. Treat wireless like any control asset with security and maintenance plans. Wireless reduces cable cost and enables measurements in hard-to-reach places. However, network planning, site survey, gateway placement, antenna is essential for reliability. Mesh topology provides redundant paths. Battery life depends on reporting rates and environmental temperature. Treat wireless devices as control assets, secure, maintain and backup device states, use wireless for monitoring non-critical variables or where wiring is impractical, and consider hybrid wired wireless designs for critical signals. Example: deploy wireless heart vibration and temperature sensor on remote spam where cabling would be expensive. Schedule periodic battery and connectivity checks. Digital communication. Modbus, Ethernet IP, Profinet. Modbus is simple and ubiquitous. Define register maps carefully. Ethernet IP and Profinet offer cyclic I/O and diagnostics over Ethernet. VLANs, QoS, and time-synchronous PTP improve determinism. Keep IP addressing, naming, and documentation disciplined. Use managed switches and monitor network health. Modbus is simple and widely supported. Define register maps and scaling carefully to avoid confusion. Ethernet IP and Profinet bring richer diagnostics and cyclic I/O over Ethernet and are suited for faster control requirements. Use VLANs, QoS, and time-synchronized point-to-point NTP where determinism matters. Document IP addressing, device names, and use managed switches with monitoring and redundancy. Example: use Modbus RTU for older analyzers into a gateway and Ethernet IP for modern I/O racks feeding the PLC with explicit production data exchange. Asset management systems. Device management software, centralized configuration, calibration, and diagnostics. It enables predictive maintenance via alerts and health indices. Integrate with CMMS to automate work orders and histories. Maintain backups of device states and templates. Restrict access and audit changes for compliance. route impulse lines to avoid traps and ensure that liquid or gas pockets won't bias the measurement, use consistent slope for drains and vents, heat trace and isolate lines in cold climates or steam service to prevent freezing or condensation. Use 3-valve for level or 5-valve manifolds for DP with isolation and equalization for maintenance and calibration convenience. Vent and drain point speed flushing and reduce downtime. Example, install a 5-valve manifold on a DP level transmitter so you can isolate and equalize the transmitter for zeroing without process interruption. Diaphragm seals and remote seals. Remote seals isolate transmitter from hot, sticky, or corrosive fluids. Field capillaries at temperature sensitive head effects. Keep equal lengths on DP pairs. Choose field fluids for temperature and vacuum compatibility. Zero the transmitter at operating temperature for best accuracy. Inspect for bugging or leaks indicating field degradations. Remote seals protect transmitters from viscous, corrosive, or higher temperature fluids by isolating process media with thin diaphragms connected via field capillary to the transmitter. Capillary lengths and field fluid introduce head and thermal effect. For DP pair, keep capillaries matched to avoid differential thermal errors. Choose field fluids with compatible vapor pressure and temperature range to avoid cavitation or vapor formation. Inspect seals periodically for bulging, which indicates internal degradation or loss of field. Example, in a hot crude application, use high temp silicone fill and match capillary length to both legs of DP level pair. DP flow varies with velocity square, so extract square root to linearize flow performance extraction ones, preferably in the transmitter to stabilize the loop. If done in PLC DCS, ensure that raw delta P signal is linear. Beware of noise at low delta P. Add damping or low flow cutoff. Document linearization location in loop sheets. Because delta P is proportional to velocity square, square root extraction linearizes flow for control and display. Perform extraction once. Usually the transmitter is bed so that the DCS receives and LED linear flow values and filtering is consistent. If extraction is done in the controller, keep the raw delta P available for diagnostics and troubleshooting. At low, delta P noise can dominate. Use low flow cutoffs or dampening to avoid spurious flow readings. Example, configure the DP transmitter to output linearized flow to the DCS and log raw delta P as diagnostic tag. Okay guys, we will continue in 15 minutes. Stay tuned. Thank you for watching. Hello. So let's continue. Uh, Topic 41, alarm management. Alarm should be actionable, unique, and timely. Avoid floats. Apply EEMUI 191 ISA 18.2 principles for rationalization. Use shelving, suppression, and deadbands to reduce nuisance. Define clear operator responses in alarm response procedures. Audit metrics, alarm rates, standing alarms, and time to acknowledgement. Time to acknowledgement. Alarms must be actionable, avoid duplicates, and not flood the operator. Rationalization using EMUA 191 ISA 18.2 is best practice. Use shelving, suppression deadbands, and delay timers to reduce nuisance alarms while keeping safety critical alarms immediate. Create clear alarm response procedures and train operators on them. Monitor alarm performance metrics, alarm rate, standing alarms, time to acknowledge, and can easily improve. Example, rationalize repeated transition high temperature alarms by adding a 10-second delay and specific operator action procedure for persistent trips. Custody transfer demand strict standard API, AGA, OAML, and audits. Flow computers apply compensation, temperature, pressure, compressibility, meter providing establishes K factors, maintain traceable records, security and sealing prevent tampering, small biases over long periods become large financial errors. Custody transfer is high stakes follow API, AGI, and OIML standards and keep auditable records. Meter providing data and K factors. Flow computers apply pressure, temperature, compressibility corrections, calculate mass or corrected volumes, and handle pulse inputs from meters and provers. Seal and secure flow computers and maintain physical and cyber protections to prevent tampering. Example, for gas sales, use an AGA-approved flow computer with schedule proving and traceable correction factors. Vibration and machinery monitoring. Accelerometers, vibration and machinery monitoring. Accelerometers measure vibration to detect imbalance, misalignment, and bearing wear. Overall velocity RMS is a quick health indicator. Spectra reveal faults. Install sensor rigidly and consistently across machines. Integrate with the shutdown logic for critical machines. Trend data and compare to ISO limits and OM baseline. Accelerometers detect imbalance, misalignment, bearing wear, and looseness. Spectra analysis reveals fault signatures. Mount sensors consistently and use same orientations and mounting bolts to ensure repeatable baselines. Define alarm thresholds tied to machine critically and integrate into control logic for protective tips where necessary. Trend data and compare to ISO or manufacturer baselines for decision making. Example, set an alarm to shut down a compressor when overall RMS vibration exceed defined thresholds and send preventive maintenance work order. Hydrocarbon detection and FGS. Fixed gas detectors, LEL, ppm toxic, and fire detectors form the FGS. Use proper placement, leak sources, low spots for heavier than air gases, maintain calibration and proof tests, sensors, age and drift, confirm that horn, beacon, and ESD actions occur per cause and effect. Ventilation and detector voting reduce false trips while preserving safety. Fixed gas detectors and fire detector must be placed at likely leak points, low spots for heavy gases and near possible ignition sources. Implement voting and delay logic to reduce false trips while ensuring safety. Critical detection triggers, ESD and alarms. Maintain calibration and proof testing schedules, gas sensors, age and drift. Verify full cause and effect that horn beacon ESD actions occur as promised during proof test. Example, place LEL sensors near pump seals and around the vapor recovery system and tie them into the FGS logic with 2 out of 3 voting for robustness. H2S measurement and safety. H2S is deadly at low ppm. Continuous monitoring is essential in sewer service. Electrochemical sensors provide ppm level detection but require frequent bumps, tests, ensure personal monitors for workers and fixed detectors near sources. Define emergency response, SCADA availability, and master procedures. Maintain calibration records and sensor replacement cycles. H2S is toxic at low ppm and can be lethal. Continuous monitoring with fixed and portable detectors is essential in sewer services. Use electrochemicals or TDL sensors depending on required sensitivity and environment. Bump test daily and replace consumable per manufacturer recommendations. Define evacuation, SCADA availability, medical response, and master procedures for detected levels. Keep training, PP, and sensor calibration logs current. Example, in Surgas well site, require personal H2S monitors for all personnel and fixed detectors near wellheads with audible, visible alarms and automatic shutdown logic for high readings. Instrumentation is key. Separator, compressors, metering. Package kits bundle instruments, valves, and controls for specific duties. Standardized transmitters and IOs for maintainability. Provide isolation, vents, and drains for every instrument. Include local indicators for quick checks during operation. Ensure documentation, PNIDs, wiring, datasheets, and test records shipped with the skid. Skid centralized instruments, valves, and controls for modularity and quicker commissioning. Standardized transmitters and IOs to ease spares and maintenance. Provide accessible isolation, vents, drains, and local indicators to speed troubleshooting. Ship complete documentation, PNIDs, wiring, datasheet, test record with the skid, and ensure traceability of components. Example, a compressor kit includes local pressure indicators, redundant transmitters, and pre-wired marshalling to simplify on-site hookup and SIT. PLC TCS interface basics. Analog card expects specific ranges. Configure scaling and diagnostics. Use engineering units in the controller to reduce HMI math. Trend K PVs and outputs to aid tuning and troubleshooting. Implement simulation modes and force management for commissioning, backup programs, and use version control for change. Analog I/O card expects specific ranges and configuration. Set input type, wiring, filter, and scaling in both hardware and software. Keep engineering units in control tags to avoid HMI, math errors, and accidental operator misinterpretation. Implement simulation modes and force management tools for safe commissioning and maintenance. Backup programs and use version control with rollback capability. Example, before commissioning, ensure the pressure transmitter input card is configured for 4 to 20 milliamps with proper filtering and tag scaling to bars on the PLC. HMI, Human Machine Interface for instruments. Good HMI show trends, PV, SP, out, statuses, and clear alarms. Use grayscale with limited color to highlight abnormal states. Provide faceplates for transmitters and valves with K diagnostics. Add quick links to loop drawings and manuals. Log operator actions for traceability. HMI should present PV, SP out, K diagnostics and trends clearly with limited color use for abnormal states. Use faceplates for each instrument so operators can quickly access diagnostics, set points, and maintenance history. Provide quick links to loop drawings and standard operating procedures, log operators, actions for accountability, design HMI with role-based access control so only trained personnel change control parameters. Example, create a valve faceplate showing position, travel time, last maintenance, and ability to force in maintenance mode with audit trail. Maintenance strategies combine preventive, predictive, and condition-based tasks. Use diagnostics from smart devices to plan interventions. Keep spares for critical transmitters, positioners, and analyzers. Train technicians on common failure modes and protocols. Review bad actors monthly and remove root causes. Blend preventive, predictive, and condition-based maintenance. Use diagnostics from smart devices to schedule interventions and reduce unnecessary outage. Keep critical spares and have swap-out plans for high criticality transmitters and positioners. Train technicians on failure modes and root cause problem solving. Track bad actors monthly and apply corrective actions. Example, use valve positioner diagnostics to schedule replacement of a staking valve before it causes process upset. Documentation and change control. Every change must be documented. Who, what, why, and when. Keep a control document set with version number. Redline in the field and reconcile to digital masters quickly. Audit loop integrity after modification. Good documentation shortens outages and improves safety. Document every change, who, what, why, when, and main version control for datasheets, logic, and PNIDs. Redline field changes and reconcile with electronic masters quickly. Delays lead to bad decision and miswiring in later phases. Audit loop integrity after modifications, and perform regression testing for safety-related changes. Example, when returning a control loop, document parameter changes, reason, test results, and rollback plan in the change control system. Okay, guys, we will continue directly without pause, without break. Cybersecurity for instrumentation. Segregate control networks from corporate IT with firewalls and DMZ. Apply least privileged accounts and multi-factor authentication for remote access. Patch carefully, testing in staging first for controller and device firmware. Monitor for abnormal traffic and maintain asset inventories. Backup configurations offline and practice restoration drills. Segregate control networks from corporate IT with firewalls, DMZ, and jump host for remote access. Apply least privilege and multi-factor authentication to sensitive systems. Patch carefully, test firmware and controller changes in staging before plant rollout. Maintain an up-to-date asset inventory. Monitor for anomalous traffic and keep backups offline ra- to recover from ransomware or corruption. Example, restrict remote PLC programming to specific management VLANs with jump servers and MFA and log all sessions. Common field mistakes to avoid. Reversing AHL site on DP transmitter skews, reading and trips controls. Shared shields or grounds create loops and noise. Missing equalization steps damage impulse lines and seals. Over-tightening lens cracks glass pH electrodes. Skipping bump test on toxic gas sensors creates life-threatening blind spots. Common mistakes include reversing HL on DP transmitters, sharing shields, grounds, creating loops, failing to equalize impulse lines, over-tightening pH electrodes, and skipping bump tests on toxic sensors. These simple errors cause big reliability and safety issues. Confirm wiring at marshalling and test field devices before startup. Example, a DP transmitter installed with reversed impulse line showed negative level and tripped a pump. Swapping the impulse lines fixed the logic without hardware replacement. Checklist pre-startup essential. Verify tag numbers, ranges, and alarm set points against the latest datasheet. Check polarity, continuity, and insulation resistance of field cables. Prove valve stroke erectly with correct fail action. Confirm interlock logic, trips, and bypass management. Record as found as left result with signature from all disciplines. Before startup, verify tags, ranges, alarm set points, cable polarity, continuity, insulation resistance, and valve fail action. Perform loop checks from field sensor to DCS. Simulate trips and record as found as left values with responsible signets. Confirm interlocks and bypass management are correct and that documentation is current. Example, before first oil, performance a pre-start checklist covering all safety and control loops. Record results and obtain discipline sign-off. Lastly, career practice. From tech to engineer. Master loop drawings, then move to control strategies and root cause analysis. Learn standards and how they apply in your plant. Practice tuning and valve sizing on real data sets. Lead FIT, SIT, and close bench items methodically. Document knowledge, playbooks elevate teams and reduce repeat failures. Move from technicians to engineers by mastering loop drawings and field devices first. Then learn control strategies, safety standards, and root cause analysis. Practice sizing, tuning, and diagnostics on real data sets and lead FIT, SIT to gain systems level understanding. Document lessons learned into playbooks and procedures. Teaching others is the fastest way to level up. Example, take ownership of a small-scale project from FAT through SIT and commissioning. Document all decision and post-mortem lessons to show leadership and systems thinking. Conclusion to practical instrumentation study guide. We have now covered the essential foundations of practical instrumentation, from measurement fundamentals and flow technologies to control strategies, safety systems, and career practices. With this knowledge, you are better equipped to troubleshoot real-world problems, make smarter design and commissioning decisions, and grow from hands-on technician work to engineering-level responsibilities. Remember, instrumentation is not just about devices and loops. It's about ensuring safe, reliable, and efficient operations in every project you work on. The more you practice, the more confident you will become in applying these principles in the field. Thank you for joining this study journey. If you found this course helpful, please like the video, leave a comment with your thoughts or questions, and don't forget to subscribe to my channel for more tutorials on instrumentation, automation, PLCs, and commissioning practices. Your support helps me create more valuable content for learners like you.